My name is Rosario Gerhard. I am a professor at the Georgia Institute of Technology, and today I'm going to be talking about a tutorial entitled, What is Impedance and Dielectric Spectroscopy? This technique is a technique that uses alternating current and can be used to characterize all types of materials and devices. I will be talking about the fundamentals and giving some examples, and then eventually show some real data that was collected in my laboratory over the last 35 years. I am currently writing a textbook to be published by a well-known publisher, and I hope you enjoy what is being presented. The tutorial will be videotaped in 2 different parts, and this is the beginning of the first part. Thank you. So, as mentioned over here, impedance spectroscopy is a technique that involves the measurement of the current, voltage, and phase angle over a wide frequency range, and it is, of course, taken by dividing the voltage as a function of frequency and the response of the current, which gives you a real and an imaginary part. In general, we use the impedance magnitude, which is the square root of the real squared plus the imaginary squared, and the phase angle is the differential between the voltage and the current, and that is normally taken by Z double prime divided by Z prime. Over the years, I'm actually a professor of material science and engineering, but I worked with a solid-state physicist. So my research is a little bit at the intersection of physics, electrical engineering, and material science. So over the years, I have worked with metals, alloys, intermetallics, many ceramics and composites, polymers and their composites, as well as semiconductors and devices. And so, by necessity, I look at many different electrical methods, such as for-probe DC resistivity. I look at the dielectric properties, the AC conductivity, and the main topic of this presentation, which is impedance spectroscopy. Additionally, I also employ some optical and magnetic spectroscopies and microscopy to measure the underlying structure of the material, as well as X-ray and neutron scattering methods. And more recently, I have also done some computer simulations using CONSOL. So why is it necessary to really characterize a material or a device using more than one type of test? The reason is that regardless of whether the signals are actually going through a device or going through a heterogeneous microstructure, the actual arrangement really can control the properties. For example, the image here on the left has the conducting phase in isolated pockets, whereas the one on the right has the conducting phase connected. And so this material has 9 orders of magnitude lower resistance than the one on the left. So let's start with the basics. So when we look at impedance, we want to first look at the impedance magnitude. And as shown on the graph here on the left, the red line, which is frequency independent, is representative of that of a resistor. The blue line shows the impedance. Please note that this is on a log scale. It's going from 10 to the minus 3 to 10 to the plus 12. This is arbitrary. These are just simulated data. But the point is that as you increase the frequency in a capacitor, you will always see the magnitude of the impedance vector go down as you increase the frequency. In contrast, for the inductor, which is represented by the green line, you have the impedance actually increasing with frequency. These go together with the phase angle, which I described in the earlier case. For resistors, the phase angle is 0. For capacitors, the phase angle is minus 90. And for inductors, the phase angle is plus 90. Generally, most people who use the technique of impedance spectroscopy are actually using a method known as EIS, or electrochemical impedance spectroscopy. And one of the most typical methods that is actually used to interpret the measurements is the Randall circuit. And basically, what you get is in the complex impedance plane, you normally get a semicircle, which is actually associated with the formation of a capacitance that is formed at the surface of the material, which is exposed to a conducting liquid electrolyte. I want to point out that what I'm talking about here has nothing to do with this type of response, because what you're measuring here is a reaction layer on the material rather than the response of the material itself. However, this particular topic is very useful for sensors, and I will not be saying very much about sensors today. So getting back to the idea of the magnitude of the impedance vector, if you take again the Randall circuit, this is what the impedance vector looks like. You have the high resistor going down due to the capacitance to another lower value resistor. And if you look at the phase angle, you see an increase and then a decrease as well. So now I'm going to illustrate starting from the simplest possible equivalent circuits. So we will start with an RC circuit in parallel. And when you have an RC circuit in parallel, these numbers were calculated using the values at the top, 10,000 ohms and 1 picofarad. You essentially, if the frequency of the equipment specifications is sufficiently high, then you may be able to get a complete semicircle and be able to detect that resistance of 10,000. This is, as I said, representative of a relatively insulating material. And then on the magnitude of the impedance vector, we have both the resistor and the capacitor part, which I showed you earlier, and then on the phase angle as well. Now, if we switch to a resistor and an inductor in parallel, we again get a semicircle, but note that this semicircle is in a different position than the semicircle for the RC circuit. This is not something that is normally described anywhere, but that's what I intend to put in my book. On the magnitude of the impedance vector, you do see the inductor going up and then the flat region related to the resistor. To the resistor. And then finally, we have an LC circuit in parallel. And when you look at it in the complex impedance plane, you basically get what appears to be no information. There's actually data here, but because they are both on the y-axis, we only see what appears to be a line. There is no resistance, so this is actually at 0. And you see the increasing portion for the inductor and the decreasing portion for the capacitor. And then this is, of course, representative of resonant behavior, which we do see in certain types of devices and materials. So the generalized trends are the log of the impedance vector versus the log of the frequency is flat for resistors, increases for inductors, and decreases for capacitors. And then the theta angle, the phase angle, is positive for inductive circuits and negative for capacitive circuits. For the complex impedance plots, we only get semicircles in the case of RC in parallel in the upper right-hand quadrant, and for LR in parallel on the lower right-hand quadrant. And so I have come up with this new nomenclature, and let me explain why the RC is put in the first quadrant. The reason is that the majority of experiments that have been conducted were originally started with materials that were fairly insulating. And so the majority of publications related to impedance show semicircles on the first quadrant. But there are more conducting materials that, of course, will have data on the fourth quadrant. And then there's also data on the second and third quadrant, but that's a more advanced topic, which we will not be talking about today. So one important concept that we need to know about is the time constant. Any one of these different graphs The mathematics tells you something, but you really need to look at this graphically so that you can fully understand. And this is why I spend so much time showing what the graphs look like. Obviously, the time constant value depends on a number of points. One is what circuit elements are present, whether they are in parallel or in a series arrangement, what are the values of those individual circuit elements, and what electric function is being used. So far, I've only talked about the impedance. So the time constant determines at what frequency one can detect a peaked function, because omega is equal to 2 pi times f. And so f is the actual measurement frequency. So for parallel RC circuits in the complex impedance plane, the time constant is obtained by multiplying the resistor in parallel with a capacitor in parallel. For RL circuits, it is the ratio of the inductor in parallel divided by the resistor in parallel. So what happens then if we have multiple of these circuits? Well, again, as I indicated, we have done far more work with RC circuits than with RL circuits. So I'm first giving you an example here for a series of RC circuits, which are parallel RC circuits. And one of the important things to keep in mind is that depending on the values of the resistors, and this is keeping the capacitors to be the same value, which are 3 orders of magnitude apart, if the resistors are equal, you get two semicircles of identical value. If one of them is a lot smaller than the other, depending on which one it is, you will get a large semicircle and another one, a small one. If they are in the reverse, the position of the small and the large one, of course, shift. And if the values are sufficiently different, one of the semicircles may be swallowed by the other. So you do not know which one, whether you have more than one process there or not. So before continuing with this, I want to show you, or I want to describe to you how you get the geometric capacitance. You first determine the size of the semicircle, which gives you RP. Then you locate the maximum on the imaginary impedance axis. And then you set omega tau equals 1 and substitute for the value of the tau, and then you solve for CP. If the capacitance value that you determine by doing that does not match the expected capacitance of the particular material or device, then you are not measuring the properties of that particular material or device. You may be measuring some surface phenomena. So that's an important point. Okay, so I have given you a lot of information about the parallel circuits. So let's say a little bit about series circuits. When we have a resistor and an inductor in series, if we plot the complex impedance, we no longer have semicircles. We get this line going into the fourth quadrant. If we look in the magnitude of the impedance vector and the theta angle, we see the trends that we have seen before. I want to state that this is representative of highly conducting materials, and it is observed in a number of situations. But we don't see a semicircle. Most people who want to use impedance spectroscopy are enamored of seeing a semicircle in the complex impedance plane. You do not see one if you happen to have a resistor and an inductor in series. So this is where converting to the other dielectric functions becomes useful, because that allows you to see semicircles in some of the other functions, which we can actually see here. This is continuing with a resistor and inductor in series. Lo and behold, if you convert it to admittance, admittance is the inverse of impedance, you now see a beautiful semicircle. And for the real and imaginary part, we see a sigmoidal shape for the real part, and we see a peaked function for the imaginary part, okay? So this tells you that there is a process going on which is a function of frequency, but you do not see it in the impedance. You see it in the admittance. So to go quickly, I will say that here is the time constant for the imaginary admittance case, which is RCSCS, the resistor and the capacitance that were in series, or LS over RS if we are looking at the RS-LS circuit. So what happens if we combine a resistor and an inductor type resistor, LR and RC time constants? Well, the actual time constant makes a huge difference. Again, if we have the resistors have the same value, we will get a complete semicircle, and one of them, the frequency will increase in one direction, and the other one, it will start in a different position. If the values of the resistors are different enough, then you will see one of the semicircles below the axis or above the axis, depending on which one is the small one. In contrast, if the time constants are in reverse, the LR time constant is greater than that of the resistor, you get a totally different behavior. So now you begin to see the beauty of actually taking a look at many of these different ways of interpreting the same data. So what are the challenges? Well, using only the impedance formalism, it is difficult to assess whether only one or more processes are occurring. The complex equivalent circuits can have many potential time constants, both in series and in parallel. And one need not get semicircles in the impedance plane in order to utilize this technique. And one must consider the other dielectric functions. And finally, it is useful to use logarithmic plots because when the values are very, very different, you need to be able to see if you have some other features that you may have missed. So now I'm going to actually show you the relationship between impedance and dielectric spectroscopy. I should mention that, of course, dielectric measurements have been made since the 1800s. And the conditions under which dielectrics are measured are generally different than those where impedance is measured. But equipment has been getting a lot better, and it's now possible to actually use measurements done in impedance and convert them into permittivity or vice versa. And so what I have here is essentially the complex permittivity plane, which everybody knows that if you have a Debye circuit, you are going to get a semicircle. And of course, if you change the value of the time constant, then you are going to change the size. And this is, of course, accompanied by a real sigmoidal-shaped curve and a peaked function in the imaginary permittivity or dielectric constant. Now, I am also including the value of the complex impedance here, and you can see that as you change the ratio, in some cases, you don't really see a clearly defined impedance semicircle, but in others, you do, like in this blue case. So why is it that we need to look at all these different functions? I've mentioned impedance, admittance, now dielectric permittivity. And the reason is that all materials contain charged objects, beginning with atoms. Atoms have protons and they have electrons. So in the presence of an electric field, they're going to separate. The center of positive charge is going to be in a different position to the center of negative charge. And depending on the feature sizes, the change will occur at a different frequency. And this, of course, will be accompanied by a dielectric permittivity peak in the imaginary function. And all materials, regardless of where they are, even if they are metals, they undergo electrical polarization. Okay, so here's a list of the polarization mechanisms that can be observed. In metals or any other conducting materials, the primary polarization method will just be electronic polarization, but you may also have space charge at the contacts. Semiconductors, you will get electronic and ionic polarization depending on the composition. You may also have space charge at the contacts. For ceramics, you get the same thing, but now you, in addition, have internal boundaries because these materials are usually polycrystalline. With polymers, same thing, but we now need to consider the polymer conformation. And if they happen to be conducting, you also have to worry about space charge formation. And of course, with composites, you can have any combination of these, in addition to the effect of the orientation of the features or the interfaces with respect to the direction of the electric field. What I show in this particular slide is that changing the magnitude of the impedance can actually determine whether you can or cannot see the permittivity response. I am not including any kind of DC conductivity over here, and all the data basically overlaps, but the frequency at which you're going to see a peak shifts to a higher frequency the lower the impedance of the system is. And when you conduct measurements, what size contacts you use can actually dominate your measurement. And so here's data that was calculated for fairly insulating films. If you only look at the complex impedance plane, you can only see 2 semicircles. All the other ones are hidden right in the center there. Whereas if you look at it on a log-log scale, you can take log, making sure to take the absolute value because you can't take negative numbers. And you can actually see, as you increase the size of the contacts, you definitely see a shift in all of the peaks, which you could not see over here. Now, this brings me to the next important point, which is the specifications of the equipment that you use. A lot of times, we assume that by making the measurement, we need to have an idea of what kind of resistance and what kind of capacitance we expect out of a material or a device. And I want to point out that most equipment is unable to really measure resistance greater than about 10 to the 14 ohms. It's very difficult to get that measurement. Likewise, with capacitance, you have the opposite situation. Most systems will not be able to measure a capacitance smaller than 10 to the minus 17 farads. So if your setup requires either of these extremes, what you get is not going to be representative of what you are hoping to be measuring. So what are the material factors? In summary, whether the material that you're measuring is mostly conducting or insulating, that will determine what you're able to get. Whether they contain voids or pores, what their size and shape is. There's a lot that I'm summarizing here, which I haven't yet presented. I will give you some examples at the end. Whether you have presence of polar molecules. For example, bulk water likes to go inside materials, and that changes the electrical response. Whether you have permanent dipoles or organic chains, whether you do heat treatments. The temperature in the atmosphere can totally change the response of a particular material or device, and so on and so forth. And so this is just to show you, this is fairly early measurements. This was actually done for my PhD thesis way back in 1983. But here we get semicircles for cerium dioxide doped with lanthanum oxide and scandium oxide. And these materials were of interest as solid electrolytes in fuel cells for high temperature solid oxide fuel cells. And one of the unique things that we did is that with impedance, we were able to separate the behavior of the bulk grains, which are shown, there are 2 examples over here, and what the properties of the boundary regions are.